Welcome to a lesson on simplifying radical expressions without fractions. A radical is not simplified if the radicand contains perfect nth root factors. So for example, if we want to simplify the square root of 8, remember for a square root the index is 2, so if 8 contains perfect square factors, this will simplify. And since 2 squared equals 4, 4 is a perfect square, and since 4 is a factor of 8, this will simplify. So we can write this as the square root of 4 times 2. And if we want, we can use this property here to write this as the product of two square roots. The square root of 8 is equal to the square root of 4 times the square root of 2. And the square root of 4 simplifies perfectly, since 2 times 2 equals 4. The square root of 8 simplifies to 2 square root 2. But it's not always easy to identify the perfect nth root factors of a radicand, so let's talk about a method that we can use to simplify radicals. We're first going to write the prime factorization of the radicand, and then we're going to circle the perfect nth root factors, which means we'll circle the factors in groups the same number as the index. For example, if it's a square root and the index is 2, we'll circle groups of 2 equal factors, and if it's a cube root, we'll circle groups of 3 equal factors, and so on. Then the circled factors are the perfect nth roots that can be simplified, and the factors not circled will remain under the radical. And then we'll finally write the radical in simplified form. But there is one more thing to remember when working with variables. When simplifying radicals, if the index is even and the radicand has variables that simplify, we must include an absolute value around the simplified variables with odd exponents to ensure that the variable is non-negative. And we'll see this in our examples. Let's begin by simplifying the square root of 72. Again, because the index is 2, this will simplify if 72 has perfect square factors. So to help us find those perfect square factors, we're going to write the prime factorization of 72. 72 is equal to 9 times 8. 9 is equal to 3 times 3. 8 is equal to 4 times 2. And 4 is equal to 2 times 2. So the prime factorization of 72 will contain 3 factors of 2 and 2 factors of 3. So we're going to write this as the square root of 2 times 2 times 2 times 3 times 3. And now again, because the index is 2, we will now circle groups of 2 equal factors, which are the perfect square factors. So here we have 2 factors of 2 and 2 factors of 3. These are the perfect square factors that will simplify. So the square root of 2 times 2 will simplify to 1 factor of 2, and the square root of 3 times 3 will also simplify to 1 factor of 3. And we're still left with the square root of 2. Of course, 2 times 3 is equal to 6, so the simplified form of square root 72 is 6 square root 2. Now I do want to point out that if we were able to recognize that 36 is a perfect square and also a factor of 72, it would save us some time if we just wrote square root 72 as square root 36 times 2 and recognize the square root of 36 is 6, giving us 6 square root 2. But again, it's often difficult to identify the perfect nth root factors when simplifying radicals, so the prime factorization method is very helpful. Now let's simplify the cube root of 125. Notice here, because we have a cube root, we'll be looking for groups of 3 equal factors. So let's write the prime factorization of 125. Well, that's 25 times 5, and 25 is equal to 5 times 5. So notice that 125 is equal to 3 factors of 5. So we can write this as the cube root of 5 times 5 times 5. And because the index is 3, notice how we have 3 factors of 5, so we're circling all of these factors, which means this simplifies perfectly 2 just 1 factor of 5. Now let's take a look at some radicals that contain variables. Here we have the square root of 27 x to the 4th y to the 7th. Again, the index is 2. Let's write this out in prime factored form. So we'll have the square root 27 is equal to 3 times 3 times 3. X to the 4th means we have 4 factors of x. Y to the 7th means we have 7 factors of y. And now because the index is 2, we will now circle groups of 2 equal factors. So there's 2 3's, 2 x's, 2 x's, 2 y's, 2 y's, and 2 y's. All of these circled factors represent perfect square factors of the radicand. And now to simplify this, we'll take one factor from each group. So this will simplify to 1 factor of 3. Notice how we have 2 factors of x, again 1 from each group, and then 1, 2, 3 factors of y, again 1 from each group. We'd be left with the square root of whatever is not circled, which is 3y. So this would be 3 x to the 2nd, y to the 3rd, square root 3y. And here's where the absolute value comes into play. Notice how the index is even because we have a square root, and the simplified part has a variable containing an odd exponent, y to the 3rd, which must be positive, and therefore we must include at least y to the 3rd in an absolute value. But often you'll see the absolute value around the entire expression outside the square root. But it could be this, or it could also be 3x to the 2nd, which we know has to be positive, absolute value y to the 3rd, square root 3y. Either of these two forms are acceptable. Next, we have the square root of 54 a to the 3rd b to the 6th. Again, the index is 2. And then for the prime factorization of 54, 54 is equal to 9 times 6. 9 is equal to 3 times 3. And 6 is equal to 3 times 2. We have 3 factors of a and 6 factors of b. And again, the index is 2. So again, we'll circle groups of 2 equal factors. Here's a perfect square factor, here's a perfect square factor, as well as here, here, and here. And now we'll simplify, taking one factor from each group. So we have 1 factor of 3, because the square root of 3 times 3 equals 3. 1 factor of a here. Notice how we have 1, 2, 3 factors of b, and we're left with the square root of 3 times 2 times a, or 6a. So we have 3a b to the 3rd times the square root of 6a. Again, the index is even. We have odd exponents on the variables here, a to the 1st and b to the 3rd. So we must have absolute values around 3a b to the 3rd. We don't have to include the 3, but it's not wrong to. Again, this assures that a b to the 3rd would be positive, which must be true because the index is even. Let's take a look at 2 more examples. Here we have the cube root of 16x to the 5th y to the 9th. In this example, we'll take a small shortcut when it comes to finding the perfect cubes of the variable factors. So we have the cube root of 16, which is equal to 4 times 4. Each 4 contains 2 factors of 2, so we have 4 factors of 2. Now for x to the 5th, because we're looking for groups of 3 equal factors, let's use our properties of exponents and write this as x to the 3rd times x to the 2nd. Notice x to the 3rd represents our group of 3 x's. And then for y to the 9th, we can write this as y to the 3rd times y to the 3rd. That would be 6 factors of y, and we still have 3 more. Again, notice how we're making the exponent match the index, but of course we could still write out 5 factors of x and 9 factors of y. Now we'll circle groups of 3 to represent the perfect cube factors. So there's a perfect cube, there's a perfect cube because we have raised to the 3rd power, as well as here, here, and here. And again, each group will simplify to 1 factor. So we'll have 1 factor of 2, 1 factor of x, 3 factors of y, which would be y to the 3rd, but I'll write y times y times y. And then we have the cube root of 2 times x squared, or 2x squared, leaving us finally with 2x y to the 3rd times the cube root of 2x squared. Now because the index is odd, we don't have to worry about the absolute value. Let's look at one more example. Notice here we have the 4th root of 16x to the 4th times the quantity x plus 2 to the 5th. So because the index is 4, we're looking for groups of 4 equal factors. We already know 16 is 2 to the 4th, or 4 factors of 2. We have x to the 4th, which is already a group of 4 equal factors. And then for the quantity x plus 2 to the 5th, we can write this as 4 factors of x plus 2 times 1 more factor of x plus 2. This would be the 1st. Now because the index is 4, we're looking for groups of 4. Here's a group of 4, here's a group of 4, and here's a group of 4. So we have 1 factor of 2, 1 factor of x, and 1 factor of x plus 2. We're left with the 4th root of 1 factor of x plus 2. And again, we have an even index. This is x to the 1st and the quantity x plus 2 to the 1st. So we do need absolute values around at least the variable parts. Let's go ahead and write this as the absolute value of 2x times the quantity x plus 2, absolute value 4th root of x plus 2. I hope you found this helpful. Next we'll take a look at simplifying radical expressions that contain fractions.